my talk is about data security for AI models in computer vision and autonomous vehicles. I'm an associate professor of computer science and engineering at WashU, Washington University in St. Louis. So the perspective of this talk is going to be fundamentally about trustworthy AI. How do we know we can trust AI to do the right thing in situations where the stakes are relatively high, such as autonomous driving? We know that autonomous driving is on the horizon. There's been a great deal of progress. What we don't understand still quite well today is exactly what kinds of realistic vulnerabilities that are exhibited by AI systems in autonomous driving, as well as more broadly than this. Okay. Now, a number of the vulnerabilities that have been explored to date, have been understood to date, arrives in perception, particularly in issues such as object detection and recognition. For example, if you want to be able to detect a hazard, such as whether there's a traffic light or a stop sign or another car on the road, can you do this successfully? And by successfully, we mean overwhelming fraction of the time to avoid accidents. So that's the subject of this talk. Okay, so kind of the background is a set of core tasks for computer vision in autonomous driving, which have to do with a combination of image classification and object detection. So for example, you have road signs. One of the possible goals of an autonomous vehicle is to be able to know road signs as it observes them through its visual system, such as a camera or a series of cameras. So for obviously critical reasons, it needs to know that there are, for example, stop signs in front of it. Alternatively, it needs to know that there are other cars or trucks or pedestrians or anything else going on the road as it's driving. So it's pretty clear that these kinds of tasks are fundamental for the car, for the autonomous car, to be able to make the correct decisions while it's driving. And the challenge is that, as we've recently discovered, even the best state-of-the-art models of perception, of AI-based perception, are susceptible to a variety of attacks. So let's take a look at a very simple example of such attacks that have become popularized a few years ago. It's the Panda example. It had nothing to do with autonomous driving in and of itself, but we'll get back to that issue shortly. Okay, so in the Panda example, you have an image of a panda, which is classified correctly as a panda by a state-of-the-art deep neural network, which is the state-of-the-art class of tools that are generally used for visual perception. So let's just call it AI-based perception. So here, everything is working great. However, if you add a small amount of adversarial noise, and the noise that you're seeing here is significantly amplified by about a factor of 200, so it's actually much, much smaller than this. So if you add this to the image, you get a composite image. To any human viewer, this still looks like a panda, but for the same exact neural network, which performs fabulously well when it's fed regular examples, now it's classifying this image as a given. So this has been exhibited as a challenge, and there's been a fair bit of research on these kinds of what people would call digital attacks. The challenge is that in these digital attacks that I've just talked about, you're literally changing individual pixel values, as you can see here. Like every pixel is changed somehow in an adversarial fashion, potentially, or a set of pixels directly. Okay, and typical examples that we are concerned about in the context of autonomous driving, you worry about different classes of attacks. Okay, so let me give an example of some of those attacks. Those are generally called physical adversarial examples in the literature. Okay, one example is something divorced from autonomous driving per se, but illustrates the kinds of things that you can do. Okay, here is a face recognition system. If you give it a face, it's going to correctly recognize this face as belonging to the correct individual. But it turns out that you can engineer eyeglass frames such that you can actually print them out, and then you put them on somebody else's face, and this person is able to impersonate someone else. For example, here somebody is impersonating successfully Mila Jovovich solely by wearing these physical eyeglass frames. That's what this is an example of what we commonly call physical attacks. Okay, the one that's more pertinent to autonomous driving is the following one that I'm going to show you now. So take a look at the video here. Okay, here is an actual car driving through with a detector. Okay, so here we have a stop sign on the left and the right. Okay, so let's take a look again. So notice that the left one is classified as speed limit 45, and the right one is correctly classified as a stop sign. even though both are evidently showing stop signs. So what's going on there? If I play this a little bit longer, you can see the left one has stickers on it. And these stickers have actually been designed adversarially so as to fool the classifier to think that it's looking at a speed limit sign instead of a stop sign for a large number of frames as it's approaching the sign. Sometimes it's correctly classifying it still as a stop sign, but a lot of the times it's not. Okay. So this is a challenge. Now, these days, there's been some ideas of using deep neural networks even as the controller itself. And the way this sort of thing would work, this was proposed by NVIDIA, among others, the way this sort of thing would work is you have a camera input into a convolutional neural network, actually really a series of camera inputs. And then the output would be actual control commands. For example, the steering angle, where do you want to turn the steering wheel? Okay. So once we actually embed such a controller in an autonomous car, we have what I would call an end-to-end autonomous driving system. It actually takes whatever the sensory information provided as inputs and ultimately actually drives a car. Okay? And so what we have shown recently is that these kinds of approaches are extremely susceptible to attack. So here's an example where, as in many scenarios, a baseline CNN-based controller, convolutional neural network-based controller works quite well. Okay, so this is where it's turning right, and it's turning right successfully. And now we show here the same scenario under attack. So what's the attack? You see the pair of the black lines that are painted on the road. Those are the lines that are going to cause what you're going to see shortly, right here, the car crashing into the fence. Okay. So, and we can engineer these kinds of attacks in ways that I'll describe momentarily. Okay, so so this kind of attack, or let's just say ways to identify visual vulnerabilities, is about painting rectangles on road pavement. Now, I just showed an example where these lines or rectangles are painted that are black, they're fairly long, but we can actually control both how many lines we paint, how far apart they are, and various other configurations of those lines. Okay. So from the vulnerability assessment perspective, we can view this as an adversary or an attacker, whose goal is to maximize deviation from correct control sequence. In this case, for example, this would be the steering angle. Now, in order to actually successfully design these kinds of configurations, we would face a few challenges. The first challenge is that the effects of the attack are actually quite complex. And in practice, they would be represented either by actual driving experiments, or in our case, by simulations. This is the examples that I showed so far, and that I'll show in the future, are based on carless simulations, which is one of the state-of-the-art simulation tools for autonomous driving. Okay, and because these effects are complex, it's difficult to efficiently design examples, and therefore it's difficult to effectively test whether vulnerabilities even exist, because you have to run lots of experiments. It's very expensive if it's real-world driving. It's even expensive if it's in simulations, because it takes many, many simulations to even find one configuration that works. Okay, so that's the first challenge. The second challenge is that cars tend to self-correct as they detect veering away from the desired path, right? As the car starts veering away, for example, on the opposing lane, its visual sequence changes, and now the car's controller knows that it needs to straighten out. It means it needs to go back into its lane. And so this kind of self-correcting behavior is a consequence of the fact that autonomous driving is this complex dynamical system. And you have to really account for that behavior in order to really understand vulnerabilities in autonomous driving systems. Okay, so one of the things that we did in addressing challenge number one is what's called the image compositing combined with gradient descent. So what does that really mean? Essentially, what happens is as follows. So you have either real driving experiments or simulations. What you can actually observe in a simulation experiment of driving is a sequence of frames as you drive correctly. And you also observe sequence of control signals. Okay, so that sequence of frames, now the question we raise is, suppose we had designed a particular adversarial pattern on the road, particular rectangles. How do we simulate efficiently superimposing these parameters onto the frames? Okay, so one thing we can do is we can use the original frames plus a small number of additional experiments to actually learn differentiable physical and color transformations between the canonical view. For example, we designed the adversarial patterns from a top-down view. So that would be a canonical view. And what we want to know is what they would look like from a perspective of the viewer of the autonomous driving perspective as it's viewing the frames. So this would mean projections onto the pavement as it's then projected by the camera in order to create the image, as well as any differences in the colors, differences between the colors that we have specified and the colors that are actually perceived once you have both painted on the pavement, plus any lighting differences, as well as the projection by the camera itself. So we can actually learn differentiable transformations for both physical and color transformations between these. And once we can do this, we can use fast and highly effective gradient-based techniques to actually automatically discover AI vulnerabilities. And we can do all of this discovery now completely offline. We don't need to run any additional simulations or driving experiments at that point to identify vulnerabilities. The only question is whether this works. Of course, it's necessarily heuristic, and the question is whether it works, and it turns out that it works extremely well. Now that's challenge number one. Challenge number two is, if you recall, you observe, the autonomous driving is dynamical system, so you do observe self-correcting behavior, and the self-correcting behavior would effectively prevent any discovered vulnerabilities from being actual vulnerabilities, because the car would just self-correct, so it wouldn't, from perspective of consequences or actually driving, it wouldn't be consequential. But it turns out that we only need to sample 3 random alternative route deviations that have small deviations from the original route for the vehicle to obtain enough diversity in the control sequences, as well as perceptual information in order to design attacks that are actually robust to even to vehicle self-correcting behavior. So in other words, we actually are able to find vulnerabilities, even though prior approaches would suggest that autonomous driving is actually robust. So it turns out that it's much more vulnerable in these simulations that we had thought before. Here are some examples, illustrations of vulnerabilities. You see here different situations, the different scenarios that we had designed these vulnerabilities for. On the left, you see a car in a scenario where it's supposed to turn left. Okay, as you see here, as it drives, it mistakenly turns right due to the adversarial pattern that we designed. Okay, in the middle, you see the car that's supposed to go straight, and it mostly goes straight except when it reaches the adversarial pattern that we designed here. And then it violates its lane and as a result crashes into the cars that are on opposite lanes. And similarly, in the rightmost one, we've designed the adversarial pattern such that the car, again, it's supposed to turn right or curve right. It's not even really a turn, it's just supposed to be curving right, but instead it fails to do so and crashes into the oncoming vehicle. And these are not just cherry-picked illustrations. We have quite a few scenarios in many situations that we can successfully design these patterns to effectively cause the car to crash or to deviate from its desired path. Okay. Some insights can be gained by just looking at some of the example scenarios with what are called deconvolutions, which essentially do the following. So you can take a look at the visual information, and what you can also look at is an activation map. So the visual information example is at the top row. The activation map is highlighted by the green. So for example, the heavier green indicates essentially what the neural network is mostly paying attention to. It's the patterns that are considered to be important. And so what you can look at is the way the patterns are similar or different in different scenarios to see what's potentially going on. So the leftmost column is the correct driving scenario with the right turn. You see pattern number 1 below. In the middle column, you see the same scenario with the adversarial pattern. You see pattern number 2 below. And as it turns out, this pattern below is similar to a scenario where the car is actually supposed to turn left instead of turn right. And what appears to be happening is that the visual system is mistakenly viewing the barrier and or viewing the adversarial pattern here as if it were a barrier and the shadow cast by the barrier potentially. So it's confusing 2 semantically different scenarios to be too similar. Okay, So the question you may now ask is, okay, so we've exhibited vulnerabilities in autonomous driving. What kinds of things can we do to deal with those kinds of vulnerabilities? Okay, so there are a few challenges. One that I'll show some evidence for later is that while there are a number of approaches for state-of-the-art approaches for robust machine learning, in fact, none of them actually work to protect against these kinds of physical attacks. I'll show that shortly. Okay, so the key question is, how do we generalizably capture these kinds of physical attacks? And the way we think of this is as follows, right? So many physical attacks of interest modify objects in a scene in a way that effectively occlude a portion of the image that captures the scene, right? So this is true for the stop sign attacks, where you have stickers that are effectively occluding portions of the stop sign. In the eyeglass frame attack, you have the eyeglass frame that's partially occluding the face in an adversarial fashion. And similarly, in the attacks on autonomous driving systems that I've shown, you have these rectangles that are adversarially designed that partially occlude the scene as it would be otherwise. Okay? So the question we ask now is, how do we deal with these classes of attacks? Okay. The challenge is that all such attacks, as you saw, introduce occlusions that seem almost arbitrarily different in nature. Okay. So the key insight is that we need an abstract representation of such attacks that we can use to construct a generalized defense. Okay? And we propose the abstract representation is a very simple rectangular inclusion attack. We call it ROA or ROA. Okay, the idea is very simple. Suppose an attacker just adds a single rectangle to an image, and this rectangle is adversarial in two ways. First, we add a large amount of adversarial noise inside this rectangle. And second, we also place this rectangle somewhere in the image, in a position, in a location in the image that is maximizing prediction error. So both of those things are done in an adversarial fashion. Okay? So just to illustrate visually what this would look like, here's a face of A.J. Buckley. Here's the same face with these adversarial rectangles specifically designed for this example that successfully defeats the correct classification. This is, again, using state-of-the-art neural networks for face detection, face recognition, rather. Okay. So now, there are interesting computational challenges in computing these kinds of attacks, but it's ultimately reasonably straightforward to do it effectively, even though it's heuristic. In particular, one thing we can do is adversarially choose the best location, which we can do just by exhaustively searching it. Or we can use essentially what amounts to a loss gradient, the gradient of the loss function, to speed things up here. And we use a technique called projected gradient descent, or PGD for short, to generate very large adversarial noise inside the rectangle itself, which is also quite an effective technique for doing so. Okay, so how does this help in developing defense? We've just apparently developed a new attack and not provided any suggestion of how this could be used for defense, but it turns out that it's actually fairly direct. There's a general purpose technique for defense. It's called adversarial training. The idea is as follows. You keep incrementally learning, but what you do is you add adversarial examples until convergence, or for a fixed number of epochs. Okay, the only question in this approach is what adversarial examples to add. And that's really, as we argue, the key issue here. So in previous approaches for robust learning, what goes wrong is the way to generate adversarial examples is not generalizable if you're trying to defend against physical attacks. And what we're going to show is that these ROA attacks, these rectangular occlusion attacks, when you plug it into the adversarial training routine, that's what works. And it actually converges extremely well. Okay, so let's take a look at some of the results. Here's a plot. It's got a bunch of lines in it. Let's not worry about exactly what all of them mean. I've just color-coded the important ones, right? So state-of-the-art are these state-of-the-art robust learning approaches that are based on other threat models that I'm not going to get into the details here. Okay, as you can see, it does quite poorly. The accuracy after the attack is generally well below 50%. Now, the other thing that happens that's very bad is even for the best state-of-the-art approaches, which is marked as adversarial training here, but it's referring to sort of state-of-the-art adversarial training approaches. It loses a lot on accuracy when you don't have adversarial examples, which is also bad. Essentially, what you're doing is you're making it more robust to adversarial instances, but now you're failing a huge fraction of the time whenever there's no adversary present, which is bad in a different way. And the key observation for our approach is not only is it significantly more robust to these kinds of adversarial examples. In this case, this is the eyeglass frame attack, but it also attains robustness with minimal loss of baseline accuracy. It still works very well on non-adversarial input instances, which arguably are the most common case in practice. And this is also something we illustrated for the stop sign and some other domains. Here, again, our approach significantly better than state of the art. And nevertheless, it remains extremely effective, even on non-adversarial instances. Okay, so this just about wraps it up. So let me just close with some takeaways. So first of all, I hope I convinced you that physical threats to AI are very real. We can affect full face recognition systems. We can pull stop sign classification. We can pull end-to-end autonomous driving, and a myriad of others that I've not really discussed. And the really surprising and somewhat counterintuitive thing is that it works against systems that on the surface appear to be spectacularly good. You know, they're extremely active predictive models. They're extremely effective. And so you would not think that they would be vulnerable to these really simplistic attacks, and yet we find that they generally are. And the second takeaway is that we've developed a very generalizable, highly effective defense against many classes of these physical attacks, specifically those classes that occlude a part of the scene. Now, this is not to say that we have finished and we can defend against everything, but what we can demonstrate is that we've made significant progress in this problem. So I'll stop at this point and ask any question and field any questions.
No, that was great, Eugene. Thank you for that presentation. It's really interesting stuff. So let me remind the audience that we do have within Whova, we do have the session Q&A. I've got a number of questions already, but if you want to pop a few in there, you know, I'll make sure that we get them asked. So how prevalent are attacks today? I know that technology, you know, kind of isn't broadly rolled out. Not everyone is using this when they drive. So maybe hackers aren't, you know, fully plugged in yet. But I assume some of these tests that you're running are theoretical. But have we seen a lot of cases of adversaries out there hacking this technology?
So in visual settings like autonomous driving, we have not. Where we have seen a great deal is in cybersecurity. For example, for malware detection techniques, where we see a lot more stuff in the field, and we know that malware evolves and adapts in response to the techniques used to detect it. So we've seen this play out in a domain where there is a lot of use. So one can readily expect this to play out once we start using autonomous vehicles more broadly as well, because, you know, the techniques are now known for developing these attacks. So it's really important to be cognizant of the fact that it is possible to do this.
Yeah, so I guess one would think of it similar to any type of hacking. It's almost an arms race between the developers and the adversaries. Is that how we should be thinking about it going forward?
To a certain extent, it's going to be inevitably an arms race. You know, from an adversary's perspective, there's a cost benefit, just like from the defense perspective. So there comes a point at which it may be possible to identify vulnerabilities, but not useful to do so. So the key thing to address is the really easy ones that can be exploited, that have really high stakes, really high consequences, right? So the kinds of things I've illustrated, you know, these are easy vulnerabilities, these are sort of easy pickings. Okay, that's really what most of the concern about. Now, we don't actually fully know to what extent they transfer to real autonomous vehicles. There's been some tests to demonstrate that they do. For example, with Tesla, people have demonstrated a few times that these kinds of things actually work on Tesla. For the most part, the state-of-the-art systems are relatively behind closed doors, so we can't evaluate this directly. But the hope is that the developers are paying attention and to some extent at least trying to incorporate these defense techniques into their pipelines.
Yeah, that's awesome. So if you were to get out your crystal ball and kind of think about where this technology leads us in the next, let's say, 3 to 5 years at the Prepare 2025 conference, what do you think we'll be talking about then? What will be the main issues that are out there?
I think in 5 years, we'll still be talking about autonomous driving. I would imagine that in 5 years, we'll still be talking about some of these vulnerabilities. It's my sense that currently the primary focus is on just fielding the cars and less on their security concerns. That usually lags at least a few years. So if we're lucky, there's going to be a lot more fielding in 5 years. That may well be it may well, as a result, be the case that we'll actually see some real attacks, physical attacks that actually get deployed on these vehicles. It's hard to say. The only things that we've seen is people throwing rocks at the cars, right? Which is not exactly the same thing, and not exactly clear what to do about that. But I expect this will still be an issue. Whether it's front and center is hard to predict. It's hard to predict anything in the fast-moving world 5 years ahead. But expect that this will remain an issue in the next 5 years. For a number of reasons. One of them is also it's just a genuinely hard problem from the robustness perspective. I do expect one of the things that will, at least in the research community, that's going to be more important with time, is the following. So currently there's been a huge jump towards data-driven AI away from sort of explicit reasoning, and in particular things like symbolic reasoning. There's an expectation that some of the symbolic stuff will come back, because what we're finding is, and one of the things that these kinds of vulnerabilities are showing, is that there's a limit to data-driven AI, because that data just doesn't capture the slew of variations that you could perceive. There's just too innumerable. And so one of the ways to deal with this, and possibly to make things more robust, is to do more reasoning about what's going on in the system itself. And this includes the visual perception part of the system. I think that there's not a whole lot of that yet. I think in 5 years, there's going to be more.
Yeah, it's really neat to think about. Well, I think that's it in terms of the questions. So I want to thank the audience, and thank you, Eugene, for taking the time. I'll give you the microphone for any closing comments. But yeah, I think this is a great session. I appreciate your time.
Sure, my pleasure. Don't have any closing comments. It's been a pleasure doing this. Thanks.
All right. Thank you very much. Take care.
Bye.